Okay, let me give you some ideas on how to get a solution for the cantilevered, one of the cantilevered beam problems we looked at in class. Let me sketch it out quickly. This is the atomic force microscope application. And I'll just quickly sketch the problem out. We have simple support here. Simple support here. We had some point F out here where you had an arbitrary force applied. This was a rectangular cross-section cantilevered beam with a height h and a breadth or a width of b, and there were some set distances. The end here, this support was labeled A, this support was labeled B, so if you want to think of that as point A or 0 even, based on where you do the coordinate axes, you can call that point B. And this is some arbitrary point F. The problem, this is specified, but we don't really need to get to that point yet until we start setting things up. And so the first part of this question was coming up with an expression to calculate bending stiffness of the cantilever at this point F in terms of the force per deflection. And so, as we've talked about in class and in the book, bending stiffness, you think of that as this value K, and that's not stress concentration factor, that's a spring constant. At any given point, and maybe we should even put a little subscript of an F there, is going to be the force divided by the deflection at that point. So the force at that point divided by the deflection. So we could define this bending stiffness anywhere along this cantilevered beam. We'll pick some arbitrary point F. Once we come up with the expression, we can plug in any values that we want. And so really, before we start coming up with formulas, we want to think about what is our goal in this problem. So this is not a problem where we're calculating failure necessarily. So calculating principal stresses is not really something we need to do for this problem, although we generally, when we design something, we will need to do that at some point. So this idea of finding failure, asking this question, that's not something here. All we're looking for at this first point is finding an expression. We're not trying to calculate values yet. We're looking for an expression for K. And so what we need to be thinking about is, what does K involve? And so one thing I would recommend before you do anything on this problem is to diagram your thought process. And so we're trying, and I almost put calculate K, we're not doing that yet. What we want is we want an expression for bending stiffness K at point F. I'll put a little subscript F there. So that's really the starting point. The starting point in a problem is not to go through and start deriving things or plugging in any numbers. The starting point is really the ending point. What do you want to end up with? So now think about, what are the inputs that we need in order to calculate that? So we certainly need to know something about that force or that ratio of forces, and we need to know something about the deflection at point F. Turns out we're going to do this ratio of F over Y. F is not really determined. We're looking for a ratio of the two. And so we're going to find a ratio of these. This turns out to be part of the same task of finding both of those. But if we think about this, if F is not given to us in the problem statement, and we need to somehow find an expression that's going to relate both of these, because the amount of Y that you get depends on the amount of F applied, and that's fundamentally what's going on in this problem. So the next step in our logic chain is, what do we need to know to calculate deflection, Y? So just to make sure you're aware of this, this is, if you want to think of it, this is beam deflection. This is not, it's not angular deflection. It's not axial deflection. It's not torsional angular deflection, or what we would call twist. It's none of those things. It's beam deflection. So think, where does this Y come from? Well, it actually comes from the information you need to calculate angular deflection. So we can put theta in there. And one thing that I think would be helpful is if you remember the fact that Y of x, if we define that as the x direction and up as the y direction, so that means z would be out of the screen here. That's the integral of angular deflection. And remember, I won't squeeze it in there yet. You can separate it down how you want it. So this tells you have to calculate angular deflection. So what are the inputs that you need for that? Well, remember that EI theta of x is going to be the integral of the bending moment. And so at some point you're going to have to calculate this bending moment. Another good thing to do would be, if just to keep things clear for you, if you want to do this with singularity functions, maybe make a note, set up singularity functions, or you can do it by superposition, however you decide to do it. But this is kind of an expression to me when I grade an exam, and it's also an expression to you that you know how to do this problem. Notice there's nothing in this problem, again, that concerns stress at this point. I'm just asking for an expression to do this. So if you've done a lot of stuff in terms of thinking about the stress transformation formulas and Moore circle, you've really kind of wasted your effort, because those aren't needed, at least not yet in this question. So follow your logic train down, decide what order of things you want to do things in, and first of all, you've got to set up singularity functions. So I'm going to do it by singularity functions, because that's I think the easiest way to do beam deflection problems in most cases. And so in order to do that, we're going to have to set up a free body diagram. And so we've got some arbitrary force F at point F. We've got simple supports. And of course, the way to get started on a problem like this is we have to make sure we have static equilibrium. So the sum of forces in the Y. And we can set this up however you want, or solve it however you want. To find B, we're going to have to sum moments around 0. We'll call that little b. So this gives us our two reaction loads, and we'll do something more with those later, but the important thing right now is leave those symbolic. Putting any numbers in there at all right now is just going to lead to mistakes later on. You want to be able to see these things, and moreover, you want to be able to keep all this symbolically so you have an expression that you could use again with other numbers. So my advice is to keep things symbolic. That's just a good habit to get into. So if we set up our singularity functions, and again, this is a very simple case problem. There's not a lot of complicated loading going on there. So the singularity functions are going to be fairly simple. But this process of setting this up is going to be crucial to doing more challenging problems. Okay. I'm just calling little a 0, so this would be x minus a or x minus 0, so I'm just leaving that off. One thing to keep in mind here is because f is an arbitrary point, I could actually put f anywhere along this beam and still, because I'm using singularity functions, still have an expression that works. And that's one of the things that's nice about doing singularity functions. So right now I'm in the point of setting up my singularity. So I do my integrations. And we get to the bending moment. So there should be a 1. And then now I'm going to get angular deflection, which now involves something related to material properties and geometry. That's where that first comes into play. So EI theta plus C1. Now if we look at this beam that we have, there are no constraints or boundary conditions anywhere on angular deflection, so we can't do anything with that C1 yet. We'll take it down to the next step of deflection. This is where you have to be very careful to make sure all your constants of integration are being taken care of correctly. Okay, so this is our final expression for deflection. One thing that you'll notice here, though, is F shows up, Y shows up, so by doing some algebra we can find this ratio of F over Y. If we look at the statics, A is going to be a function of F, B is also going to be a function of F, so these A's and B's will drop out. Everything's going to be forces. F's on top, you've got the Y over here, so you can figure everything out from there. Right now, it's not a bad idea to apply your boundary conditions to get C1 and C2. So the boundary conditions we have, because they're simple supports, is we know that Y at point A and at point B are going to equal 0. So just by inspection, we plug in 0 here. That has to go to 0. Let's plug in Y at B. We're going to get this is going to be 0. This does not turn on yet. And there's where we start plugging things in. We can simplify A. It's probably best to solve for C1 first. We know that this whole thing has to equal 0. Okay, so that's the value of C1. If you want to put it in terms of F right now, that would be fine. So this is a good time to actually solve for C1. That leads us back over here. So if we put C1 in terms of F, which is kind of the goal here, you can do some manipulation. First, let's figure out what A is. We can put A in simplest terms. That's going to be distance F over distance B minus 1 is one way to put that. So now that puts B in terms of F, A in terms of F. If we go ahead and solve this through, A over 6B squared, we get this expression. So based on how you want to do it, you can get a little cumbersome. The point is being able to set up this entire expression, and we can do that, and that is really the last crucial step for this problem. So if we set up the entire expression, and we can do it, let's put it specifically at point F. So if you plug F in for that, because we want to know what is the stiffness at F, I'll put F in there. So just to point out what's going on, this term is turned on because we're past point 0. This term is turned on because F minus B is greater than 0. This term is turned on, although it's going to be 0. It's at point F, F minus F is 0. And of course this term is always on. And that's why when we get to angular and actual deflection, the singularity functions, we have these constants of integration. So if we put this whole, we do some simplification, we put this whole expression out there, it does become kind of long, but with some simplification, what you get, negative F And so this expression for any values of force F, which is an arbitrary force, any distances little f or little b, any setup that you have for a given stiffness and a given cross-section geometry, this will give you either the bending stiffness if we solve it for F over Y, or if you've got a value of F, if you have a known force F or a known distance F, it will tell you the exact amount of deflection. So let's go ahead and solve this whole expression for K. So K at F is whatever force applied by whatever deflection you have at that point. And so K is equal to F over Y. Again, this is just some algebraic manipulation. One of the key things to be doing is making sure all your units make sense. So here is your expression, or here is one expression without any specifics in there. What that expression will work for is that will work for bending stiffness for any beam with this configuration. If we've got two simple supports, we have 1 point of interest. The thing to keep in mind is that F is not necessarily being applied there. That's saying if we did apply some force there, what the bending stiffness would be at that point. And that point F can be anywhere. You would have to be told where that F should be, or you could be asked, where is the maximum or minimum bending stiffness? Find the location F that gives the maximum or minimum bending stiffness. And so here's the expression. One thing that this expression assumes, and this came from our singularities, this is assuming that the distance F is greater than the distance B. If we throw out that assumption, we just solve our singularities a little differently. Some terms will be in and some terms won't. If F is not greater than B, let's say that if F is over here somewhere, this would look different. Essentially, that term would not be turned on yet. And when we solve for C1 or C2, our boundary conditions change a little bit. So in order to get actual numbers here, if we want to get one step further, we know all of our values. For one of the in-class problems, you've got we don't really worry about the effective length of the beam, but we know that that force F, or the point F where the force is being applied, we know that that's 110 microns from the left. We know that that simple support B is at 25 microns. I is going to equal BH cubed over 12, so we have B and we have H. And so from that we can find an expression for bending stiffness that depends only on the stiffness of the material used. And so we can plug in different materials. Let me crunch this down to be an expression just based on E, and you can check your numbers against this if you'd like. So plugging in real values, we get a bending stiffness K at that point of minus 560 times 10 to the negative 12 times elastic modulus, and that's going to be in newtons per meter. That's for these given parameters. And so you realize, common sense wise, the stiffness of this cantilever beam is going to be greatly affected by what material you build it from. And in this case, it shows up very clearly in the stiffness expression. So given this configuration, you could choose a material, or you can say that a certain amount of stiffness is needed, and then you decide what materials would satisfy that. Or if you're constrained, you can say for a given material what stiffness can be offered. there are some different games you can play with changing the stiffness in terms of moving those supports around, changing the geometry of the beam and other things. But that is how to solve this particular problem. So given the way the question is posed from in class, it talks about using crystalline silicon. You'll find different values for that. You'll find values from, let's say, 130 to 169 gigapascal. If we just pick something, ballpark, 150 gigapascal, let's say, we can plug that directly into that expression for K and get a final answer. And you'll see it's on the order of roughly 80 newtons per meter. And so if you plug in these numbers, you want to get an order of magnitude value somewhere in that neighborhood.